335 million years ago, Earth looked nothing like the world we know today. Instead of several continents separated by vast oceans, nearly all the land was joined together in one enormous supercontinent called Pangea. Strange forests stretched for countless miles, giant insects filled the air, and early reptiles began exploring this changing world. Powerful rivers, towering mountains, and endless deserts shaped a land unlike anything alive today. But how did all the continents become one giant landmass? What incredible creatures lived there before the age of dinosaurs? And what forces slowly tore this ancient world apart? "335 million years ago, the land on Earth looked very different from the world people know today. There were no separate continents spread across the planet in the way they appear on modern maps. Instead, almost all of Earth's land was joined together as one enormous landmass called Pangea. This giant supercontinent stretched across a large part of the planet and brought together areas that would one day become North America, South America, Europe, Africa, Asia, Australia, and Antarctica. At that time, these lands were connected instead of being separated by the wide oceans that now divide them. The shape of the world was completely different, and the movement of life, the weather, and the natural environment all happened under conditions unlike those seen today. Pangea is one of the most important parts of Earth's history because it helps explain how the planet changed over a very long time. It is not simply a name found in geology books. It represents a real stage in Earth's past when the land existed as one connected body. Scientists have spent many years studying this ancient world because it provides valuable information about the movement of continents, the history of mountains, the spread of plants and animals, the changing climate, and the slow forces that continue to shape Earth even now. The name Pangea comes from words that mean all Earth, because it included almost every major piece of land on the planet. This name fits well because the supercontinent gathered nearly all continental land into one connected mass. Although the world looked different during that time, the same natural forces that work today were already active. The ground beneath the surface was moving slowly. Heat from deep inside the planet continued to push enormous plates of rock across Earth's surface. These movements happened so slowly that they could not be noticed over a single lifetime. Yet over millions of years, they completely changed the appearance of the world. Earth itself is much older than Pangea. The planet formed about 4,500 million years ago. During that long history, the continents did not always remain in one place. They slowly moved, joined together, broke apart, and moved again. Pangea was not the first supercontinent that existed, and scientists believe it was not the last stage in the long history of continental movement. Earlier, supercontinents had formed and separated long before Pangea appeared. Later, after Pangea broke apart, the continents continued moving toward the positions they occupy today, and they are still moving even now. The idea that continents move across Earth's surface was once difficult for many people to accept. For many years, most scientists believed that continents had always stayed where they were. Maps showed the continents separated by oceans, and many assumed that this arrangement had existed since the beginning. However, careful observations slowly began to challenge that belief. People noticed that the eastern coastline of South America and the western coastline of Africa seemed to fit together in a surprising way. The shapes were not perfect because millions of years of erosion and rising sea levels had changed the coastlines. But the general outline suggested that these lands may once have been connected. Scientists also found rocks of the same age and type on continents now separated by wide oceans. Mountain ranges ended at one coastline and appeared to continue on another continent far away. Fossils of the same ancient plants and animals were discovered in places where those living things could not easily have crossed vast oceans. These discoveries suggested that the continents had once formed a single landmass before moving apart. One of the people who helped bring attention to this idea was the German scientist Alfred Wegener. During the early 20th century, he suggested that the continents had once been joined together, before slowly drifting apart. Many scientists doubted his idea because he could not fully explain what force moved the continents. Even though he collected many pieces of evidence, his explanation remained incomplete. Years later, new discoveries about the ocean floor and the movement of Earth's plates provided the missing information. Scientists eventually understood that Earth's outer shell is divided into large rocky plates that slowly move over the softer layer beneath them. This understanding became known as the theory of plate tectonics, and it explained how Pangea formed and later separated. The surface of Earth may appear solid and unchanging, but it is actually active. Deep beneath the ground, heat rises from the planet's interior. This heat creates slow movement inside the mantle, the thick layer beneath Earth's crust. These movements help push and pull the giant tectonic plates that carry the continents. The plates move only a few centimeters each year, which seems very slow. However, over millions of years, these tiny movements add up to enormous distances. Entire oceans can open, mountains can rise, and continents can travel across the planet. When Pangea existed, it was surrounded by one enormous ocean known as Panthalassa. This ocean covered most of Earth's surface. Along the edges of Pangea, waves reached long coastlines, while the center of the supercontinent lay far from the sea. This arrangement had a major effect on climate. Areas close to the ocean received more moisture, while regions deep inside the continent often became dry because ocean winds could not easily carry water far inland. Large deserts formed in many interior regions where rainfall was limited. The weather across Pangea was not the same everywhere. Some regions experienced warm tropical conditions with thick forests and rich plant life. Other places were dry and dusty. Farther south, colder conditions existed, where large ice sheets had formed during certain periods. Since Pangea stretched across many different parts of the planet, it included a wide variety of climates. These different environments supported many forms of life that adapted to local conditions. The rivers flowing across Pangea were often very long because there were no oceans interrupting their paths through separate continents. Water traveled great distances before reaching the sea. Lakes formed in low areas, while floodplains spread across broad regions. Sediments carried by rivers settled over time and later hardened into rock. Today, geologists study these rocks because they preserve valuable records of ancient environments. Life during the age of Pangea included many kinds of plants and animals. Forests filled with ferns, seed ferns, giant club mosses, and early conifers covered many parts of the land. These plants captured sunlight and provided food for plant-eating animals. Fallen leaves and dead plants slowly built layers of organic material that, after millions of years under heat and pressure, became coal deposits found in many parts of the world today. Animal life also continued to change during this period. Early reptiles became increasingly successful because many were better suited to dry conditions than amphibians. Their eggs could survive away from water, allowing them to spread into environments that amphibians could not easily occupy. Different groups of reptiles developed many new features as they adapted to forests, open plains, deserts, and coastal areas. Some of the earliest relatives of mammals also lived during the time of Pangea. Different groups of reptiles developed many new features as they adapted to forests, open plains, deserts, and coastal areas. Some of the earliest relatives of mammals also lived during the time of Pangea. These animals belong to groups that are now extinct, but they showed features that later became common in true mammals. They lived alongside many reptiles, insects, fish, and amphibians. Each group occupied different habitats and played different roles in the natural world. The oceans surrounding Pangea contained a rich variety of marine life. Fish of many kinds swam through the seas. Coral communities supported countless smaller creatures. Shellfish, ammonites, trilobites during earlier times, and many other sea animals filled the waters. Marine ecosystems continued changing as species appeared, spread, and disappeared through natural processes over long periods. Pangea also played an important part in the history of evolution, because connected land allowed many animals and plants to spread over large areas. Species that lived on one side of the supercontinent could gradually expand into distant regions without crossing major oceans. As climates changed and environments differed from place to place, populations slowly adapted to local conditions. Over many generations, these differences sometimes led to the development of new species. Mountain building was another major feature of the age of Pangea. When continents slowly collided, the edges of the tectonic plates pushed against one another. Huge layers of rock folded, cracked, and rose upward to form mountain ranges. Some mountains that exist today began forming during the creation of Pangea. Even though erosion has worn them down over millions of years, geologists can still identify rocks that record these ancient events. The Appalachian Mountains in North America and mountain belts in parts of Europe and Africa contain rocks that once formed continuous ranges before the continents separated. Today, they are divided by the Atlantic Ocean, yet their similar ages, structures, and rock types reveal their shared history. These connections provide powerful evidence that the continents were once joined together. Earth's climate during the time of Pangea changed many times. Natural cycles affected temperatures, rainfall, sea levels, and ice coverage. Volcanic activity released gases into the atmosphere. Changes in ocean circulation influenced the movement of heat around the planet. Variations in Earth's orbit also affected long-term climate patterns. Scientists study ancient rocks, fossils, and chemical signals preserved in sediments to understand these changes. The interior of Pangea faced unique environmental conditions because it lay far from the moderating influence of the oceans. Summers could become extremely hot in some places, while winters could be much colder. Seasonal differences may have been stronger than in many coastal regions. Dry winds crossed wide areas, shaping deserts and influencing the distribution of plants and animals. Large volcanic eruptions occurred at different times during Earth's history while Pangea existed. Molten rock reached the surface through cracks in the crust, creating vast lava flows. These eruptions released gases that affected the atmosphere and climate. Thick layers of volcanic rock formed across wide areas. Millions of years later, these rocks continue to provide evidence of ancient geological activity. Earthquakes also occurred as tectonic plates moved. The movement was slow overall, but stress built up where plates met. When rocks finally broke or shifted, earthquakes released the stored energy. Similar processes continue today wherever tectonic plates interact. The breakup of Pangea did not happen suddenly. It unfolded over many millions of years. Cracks first appeared within the supercontinent as tectonic forces stretched the crust. These cracks gradually widened into valleys. Magma rose from below and created new crust. Eventually, seawater entered these low areas, forming young oceans that continued expanding as the continents drifted apart. One of the first major separations divided Pangea into two large landmasses. The northern part became known as Laurasia, while the southern part became Gondwana. These giant continents later divided again into smaller pieces that slowly moved toward their present locations. The Atlantic Ocean gradually opened between North America and Africa as new ocean crust formed along the spreading center beneath the sea. As continents drifted apart, populations of plants and animals became separated. Species that once lived together now evolved in different directions because oceans prevented easy movement between continents. This separation contributed to the remarkable variety of life found across the world today. Fossils preserved on different continents continue to reveal these ancient connections. Evidence for Pangea comes from many scientific fields working together. Geologists examine rocks, mountain belts, and minerals. Paleontologists study fossils. Geophysicists investigate Earth's interior and magnetic records preserved in rocks. Oceanographers map the seafloor. Each area of research provides another piece of the larger picture. Together, these discoveries support the understanding that Earth's continents have moved over immense periods of time. One important discovery came from studies of the ocean floor. Scientists found long underwater mountain chains where new crust forms. They also discovered that magnetic minerals inside volcanic rocks preserve a record of Earth's magnetic field at the time they cooled. Matching magnetic patterns on both sides of mid-ocean ridges showed that new crust forms at the ridges and moves outward. This process, called seafloor spreading, provided strong support for plate tectonics. Modern technology has made it possible to measure continental movement directly. Satellites using highly accurate positioning systems detect tiny changes in the location of continents every year. Although these movements are only a few centimeters annually, they match the predictions made by plate tectonic theory. This ongoing movement shows that the processes responsible for forming and breaking apart Pangea are still active today. The study of Pangea has also improved understanding of natural resources. Coal, oil, natural gas, metal deposits, and valuable minerals often formed under geological conditions linked to ancient continental movements. Knowing how continents were arranged in the past helps geologists identify areas where these resources may be found. The history of Pangea has influenced the distribution of many living organisms that exist today. Some groups of plants and animals are found on continents now separated by oceans because their ancestors lived together before the land divided. Fossil discoveries continue to reveal these ancient relationships and help scientists trace the movement of life across Earth's changing surface. Many students first learn about Pangea by looking at maps that show how today's continents fit together. While these maps offer a useful introduction, the full story is much deeper. Every rock layer, fossil bed, mountain range, and ancient coastline contains information about events that unfolded over millions of years. Scientists continue studying these clues because every discovery improves understanding of Earth's long history. The idea of Pangea reminds people that the planet has never remained unchanged. Continents have shifted, oceans have opened and closed, mountains have risen, climates have changed, and life has continued adapting through each stage of Earth's history. These changes happened through natural geological processes operating over immense periods of time. Even today, the continents continue moving. Africa slowly approaches Europe, Australia gradually moves northward, North and South America shift westward. The Atlantic Ocean continues widening while parts of the Pacific Ocean slowly become smaller because of plate movements. These changes are extremely slow, yet they show that Earth's surface remains active. Scientists believe that many millions of years from now, Earth's continents may once again gather into another supercontinent. The exact arrangement remains uncertain because continental movement is complex and depends on many geological processes that continue far into the future. What is clear is that the same forces that created Pangea are still shaping the planet beneath our feet today, moving the continents little by little as Earth's long geological history continues to unfold. The surface of the Earth has never been completely still. Deep beneath the ground, huge pieces of the Earth's outer layer have always been moving, even though the movement is extremely slow. These huge pieces are called tectonic plates. They carry the continents and the floors of the oceans. They move because of heat coming from deep inside the Earth. This heat causes very hot rock below the plates to rise, spread, cool, and sink again. These slow movements create forces that push and pull the tectonic plates in different directions. Although people cannot notice these movements during their daily lives, they continue every day and every year. Over very long periods, they change the shape of the Earth's surface and the positions of the continents. The formation of Pangea was the result of these slow but steady movements. It did not happen suddenly. It took many millions of years for separate pieces of land to move closer together. During this long period, ancient continents slowly drifted across the Earth's surface. As they moved, they sometimes collided with one another. These collisions slowly joined the land together until almost every major piece of land became part of one giant supercontinent known as Pangea. Scientists learned about this process by studying many kinds of evidence. They examined rocks found on different continents. They studied the shapes of mountain ranges. They looked at fossils of plants and animals. They measured the direction of tiny magnetic minerals trapped inside ancient rocks. They also used information gathered from earthquakes and volcanic activity. All of this evidence helped them understand that the continents were once connected and later moved apart after Pangea existed. The Earth itself is made of several layers. At the center is the inner core, which is extremely hot and made mostly of iron and nickel. Around it is the outer core, where these metals remain in a liquid state because of the intense heat. Above the outer core lies the mantle, which is made of very hot rock. Although the mantle is solid, it can slowly flow because of the high temperatures and enormous pressure found deep underground. The outermost layer is the crust, where people, animals, and plants live. The crust and the uppermost part of the mantle together form the lithosphere, which is broken into tectonic plates. These tectonic plates fit together like very large pieces covering the Earth's surface. Some carry continents, while others carry ocean floors. They are always moving, although the movement is usually only a few centimeters each year. Even though this distance is small, millions of years allow the plates to travel thousands of kilometers. The heat inside the Earth is one of the main reasons these plates move. Heat left from the Earth's formation, together with heat produced by radioactive elements inside the planet, keeps the mantle extremely hot. This heat creates slow-moving currents within the mantle. As hot rock rises and cooler rock sinks, the plates above are pushed and pulled in different directions. Sometimes two plates move toward each other. When this happens, one plate may slide beneath another if one is heavier. This process is called subduction. As one plate sinks into the mantle, it melts and becomes part of the Earth's interior once again. The sinking plate can also create deep ocean trenches, earthquakes, and volcanoes. In other places, two continents carried by different plates eventually meet. Since both continents are made of lighter rocks, neither easily sinks beneath the other. Instead, they push against each other. The rocks become folded, broken, and lifted upward. This creates large mountain ranges. These mountains continue rising while the plates keep pushing together, although wind, rain, rivers, and ice slowly wear them down over time. The path toward the formation of Pangea involved many ancient continents. These landmasses had different shapes and sizes. They moved across the Earth's surface for many millions of years before finally joining together. Their movement was not smooth or straight. Sometimes they changed direction because the forces acting on the plates also changed. At times they moved apart from neighboring landmasses, while at other times they slowly came together again. One of the earliest important landmasses involved in this process was called Laurentia. This ancient continent included much of what later became North America and parts of nearby regions. Another major landmass was Baltica, which later formed parts of northern Europe. Siberia also existed as a separate landmass. Farther south lay Gondwana, one of the largest ancient continents. Gondwana included land that later became South America, Africa, Antarctica, Australia, the Indian subcontinent, and nearby areas. These ancient continents were separated by large oceans. One important ocean was called the Iapetus Ocean. Another was known as the Rhyic Ocean. These oceans existed for millions of years, while the continents slowly drifted across the planet. As plate movements continued, many of these oceans gradually became smaller. The closing of these ancient oceans played an important part in the formation of Pangea. As tectonic plates moved toward one another, the ocean floor between them slowly disappeared beneath the continents through subduction. Year after year and century after century, more ocean crust sank into the mantle. As the oceans became narrower, the continents on opposite sides moved closer together. Eventually, the continents collided. These collisions were not quick events. They lasted for millions of years. The edges of the continents became squeezed together. Layers of rock bent, cracked, and rose upward. New mountain ranges formed during these events. The pressure changed the rocks deep underground, creating new kinds of rock through heat and pressure. One important mountain building event happened when Laurentia and Baltica collided. Their meeting helped create a larger continent called Euramerica. This collision also formed mountain ranges, whose remains can still be found today in parts of North America and Europe. Although these mountains have been worn down over countless years, their ancient roots still provide important evidence for scientists studying the Earth's past. At the same time, Gondwana continued moving across the Earth's surface. It was already an enormous landmass, but its journey was not finished. As it slowly drifted, it approached Euramerica. The ocean separating them became smaller because of continued plate movement. Ocean crust kept sinking beneath the continents until little remained between them. The final stages of bringing these great landmasses together happened during the late Paleozoic era. By about 335 million years ago, most of the Earth's major continents had joined together. This produced the giant supercontinent called Pangea. Nearly all of the Earth's land was connected into one enormous landmass that stretched across a large part of the planet. The joining of these continents greatly changed the Earth's geography. Areas that had once been separated by oceans became connected by land. Animals and plants could spread into new regions. Rivers found new paths across the giant continent. Mountain ranges continued forming where the continents had collided. Deep inside the Earth, tectonic forces remained active even after Pangea had formed. Pangea was surrounded by a vast global ocean known as Panthalassa. This ocean covered most of the Earth's surface. Along the edges of Pangea, waves reached long coastlines that stretched for many thousands of kilometers. Inside the giant continent, however, many places were located far from the sea. Because many regions lay far from the ocean, their climates became different from coastal areas. Moist air from the sea often lost much of its water before reaching the center of the continent. As a result, many inland areas experienced dry conditions. Some places became deserts where rainfall was limited. Other regions remained wetter, depending on their location and nearby mountain ranges. The formation of mountains also affected weather patterns. When moist air reached mountain slopes, it often released rain or snow before crossing the peaks. Areas beyond the mountains sometimes received much less rainfall. These changing weather conditions influenced where forests, grasslands, wetlands and deserts developed across Pangea. The movement of tectonic plates did not stop after Pangea formed. The plates continued to shift beneath the surface. Stress slowly built inside the rocks. Heat remained trapped beneath the crust. The same forces that had joined the continents together continued operating beneath the Earth's surface. Over millions of years, these forces would eventually begin pulling parts of Pangea apart, although the supercontinent remained together for a very long period before breaking into separate continents once again. Scientists continue studying the formation of Pangea because it helps explain many features found on Earth today. Rocks of similar age and composition appear on continents that are now separated by wide oceans. Fossils of the same plants and animals have been found in places that are now thousands of kilometers apart. Ancient mountain belts also line up across different continents when their past positions are reconstructed. Modern technology has greatly improved the study of tectonic plate movement. Satellites can measure the movement of continents with remarkable accuracy. Instruments placed around the world detect earthquakes that occur when plates suddenly shift. These observations confirm that tectonic plates remain active today, just as they were during the long process that formed Pangea. The study of magnetic minerals inside rocks has provided another important source of information. When molten rock cools, tiny magnetic minerals line up with the Earth's magnetic field. Once the rock becomes solid, these minerals remain locked in place. Scientists measure their direction to determine where the rocks formed millions of years ago. This helps them rebuild the ancient positions of continents. Fossils also provide valuable clues. Certain animals and plants lived over wide areas before the continents separated. Their remains became buried in sediment and later turned into fossils. Today, matching fossils are found on continents now divided by oceans. These discoveries support the idea that the land was once joined together. Ancient glaciers also left evidence behind. During parts of the Earth's history, large sheets of ice covered sections of Gondwana. As glaciers moved, they scratched rocks and left behind distinctive deposits. Scientists have found these marks in South America, Africa, India, Antarctica, and Australia. The direction of these scratches makes sense only when these continents are placed together as parts of Gondwana before Pangea fully formed. Every stage in the formation of Pangea required the steady movement of tectonic plates. No single event created the supercontinent. Instead, countless small movements continued over many millions of years. Oceans slowly closed, continents gradually approached each other. Mountain ranges rose, earthquakes shook the ground, volcanoes erupted, and the Earth's surface continued changing through the powerful natural forces operating deep below the crust. Pangea covered a very large part of the Earth's land surface during the late Paleozoic era and the early Mesozoic era. It was formed when many separate landmasses slowly moved together over a very long period because of the movement of tectonic plates beneath the Earth's surface. These slow movements continued for millions of years until the continents became connected into one enormous landmass. This giant landmass stretched across a large part of the planet and contained almost all of the Earth's dry land. The total area of Pangea is estimated to have been about 148 million square kilometers. This made it the largest known supercontinent in Earth's history. Around it lay one huge ocean called Panthalassa, which covered most of the Earth's surface beyond the edges of the supercontinent. The shape of Pangea was not perfectly round or square. It had a wide and uneven outline that changed slowly over millions of years as the land continued to move. Some parts of the coastline stretched far into the surrounding ocean, while other parts curved inward to form large bays and shallow seas. The land extended across many lines of latitude, reaching from areas close to the South Pole to regions much nearer the North Pole. Because of this great distance from north to south, different parts of Pangea experienced different climates. Some areas remained cold for long periods, while others stayed warm throughout the year. The center of Pangea was located far from the ocean. Since moist air from the sea could not easily reach these inland regions, they became very dry. Rainfall was limited across much of the interior. Large deserts developed over wide areas and remained for long periods. Wind shaped the sand into large dunes that moved slowly across the land. Many of these ancient sand dunes later hardened into sandstone after they were buried beneath layers of sediment. Today, these sandstone rocks can still be found on several continents that were once joined together as part of Pangea. Their presence helps geologists understand the dry conditions that existed in the heart of the supercontinent. The coastlines of Pangea stretched for many thousands of kilometers. They followed an uneven path with many curves, narrow points, broad coastal plains, and rocky shores. In some places the land dropped sharply into deeper water. In other places the coast sloped gently into shallow seas. Rivers carried sand, mud, and small stones from inland areas towards the coast. These materials settled near the shoreline and slowly built wide layers of sediment. Over long periods, these sediments became solid rock, preserving signs of ancient environments that once existed along the edges of the supercontinent. One important feature of Pangea was the large sea known as the Tethys Ocean. This body of water lay along the eastern side of the supercontinent and reached into the land through broad openings. The shores around the Tethys supported many kinds of marine life because sunlight reached the shallow water, allowing many living things to grow and reproduce. Coral reefs formed in warm, shallow areas, while shells, fish, and many other sea creatures lived nearby. Rivers flowing into the Tethys carried fresh water and sediment from the land, creating wetlands and coastal plains in some places. The mountains of Pangea formed as continents collided with one another. When two large landmasses pushed together, the rocks along their edges were squeezed, folded, and lifted upward. This process created long mountain ranges that stretched across great distances. Some of these mountains were among the highest on Earth during that time. Their peaks were worn down slowly by wind, rain, rivers, and changes in temperature. Broken pieces of rock moved downhill into valleys where rivers carried them away. These materials later became new layers of sediment in lower areas. One of the best-known mountain systems formed during the creation of Pangea was the Central Pangean Mountains. This long chain extended across the middle of the supercontinent and influenced weather patterns over a wide area. The mountains blocked some moist air from reaching inland regions. As a result, many places beyond the mountains received very little rainfall. Dry conditions continued over large areas, helping deserts expand across the interior. The Appalachian Mountains in what is now eastern North America were once connected with mountain ranges found in parts of Europe and northwestern Africa. Before the continents separated, these mountains formed one continuous system. Today they are divided by the Atlantic Ocean, but the rocks within them show many similarities. Geologists study the age, structure, and minerals of these rocks to understand how the continents were once joined together. The interior plains of Pangea covered enormous areas between mountain ranges and coastal regions. Many rivers crossed these plains, carrying water during wet seasons and leaving behind fertile sediment where flooding occurred. Some rivers flowed for great distances before reaching the sea. Others ended in inland basins where water collected for a time before drying under the hot sun. Lakes appeared in some low places during wetter periods, while other lakes disappeared when rainfall decreased. The deserts of Pangea became one of its most important geographic features. Since much of the land lay far from the surrounding ocean, dry air remained common across the interior. Rain clouds rarely reached many regions because most of their moisture had already fallen closer to the coast. Strong sunlight heated the land during the day, while clear skies allowed temperatures to fall at night. These daily changes affected rocks, causing them to crack into smaller pieces over time. Wind carried dust and sand across the dry landscape, slowly changing the shape of the ground. Plants found it difficult to survive in the driest parts of Pangea. Only certain kinds of vegetation could live under these harsh conditions. In places where rivers flowed or groundwater reached the surface, plants formed narrow belts of green across the otherwise dry land. During wetter seasons, some grasses, ferns, and seed plants spread into nearby areas before the dry conditions returned. In regions with greater rainfall, forests covered large parts of the landscape and supported many different kinds of animals. The southern parts of Pangea experienced colder climates during some periods because they lay closer to the South Pole. Evidence of ancient glaciers has been found in rocks from what are now parts of South America, Africa, India, Australia, and Antarctica. These glaciers moved slowly across the land, scraping rocks beneath them and leaving marks that remain visible today. As the climate changed over millions of years, the ice gradually melted, allowing new plants and animals to spread into areas that had once been covered by glaciers. Panthalassa surrounded Pangea on almost every side. It was the largest ocean on Earth during that time and covered much more area than the supercontinent itself. The ocean stretched across great distances without interruption. Its waters influenced weather along the coastlines by providing moisture for clouds and rainfall. Strong winds moved across the ocean, creating waves and currents that carried heat and nutrients through the water. These ocean currents affected marine life as well as the climate of nearby coastal regions. The shores of Panthalassa included many different environments. Some coastlines were rocky, with steep cliffs facing the sea. Others consisted of wide, sandy beaches where waves deposited sediment. In some places, broad tidal flats formed as the sea advanced and retreated with changing tides. Wetlands developed where rivers entered the ocean, creating rich habitats for many forms of life. Shells, fish, early marine reptiles, and countless small organisms lived in these waters. The ocean floor beneath Panthalassa was constantly changing because of movements within the Earth's crust. New oceanic crust formed along underwater ridges, where molten rock rose from deep inside the Earth. Older sections of the ocean floor slowly moved away from these ridges and eventually sank beneath the edges of continents through the process of subduction. These movements continued throughout the lifetime of Pangea and played an important role in shaping the supercontinent itself. The edges of Pangea were active in many places because tectonic plates continued to move even after the supercontinent formed. Earthquakes occurred where rocks suddenly shifted along faults. Volcanoes appeared in regions where molten rock reached the surface. Thick layers of volcanic ash sometimes covered nearby land, while flowing lava created new rock layers. These events changed the local landscape and added fresh material to the Earth's crust. Large river systems drained different parts of Pangea. Water flowing from mountains carried broken rock, sand and mud into lower areas. Rivers often changed their paths as sediment built up along their channels. Floodplains developed beside many rivers, receiving fresh layers of fertile soil whenever flooding occurred. Over time, these sediments became important records of ancient environments, preserving plant remains, footprints, and other evidence of life that existed across the supercontinent. Earth's climate during the age of Pangea was shaped by the unusual arrangement of the planet's land and oceans. During this period, almost all of Earth's continents were joined together into one enormous landmass. This single continent stretched across a large part of the planet, while one vast ocean surrounded it. The size of this landmass changed how heat, moisture, wind, rainfall, and seasonal conditions spread across the world. Every part of the continent experienced climate in a way that was connected to the presence of this huge area of land. The climate was not the same everywhere. Some regions were very dry, some received heavy seasonal rain, some remained warm for most of the year, while others experienced cold winters and changing seasons. The position of Pangea on the globe played a major part in determining its climate. Parts of the supercontinent lay close to the equator, where sunlight reached the surface more directly throughout the year. Other parts stretched into higher northern and southern latitudes, where the angle of sunlight changed with the seasons. These differences in the amount of sunlight created different climate zones across the continent. Areas near the equator generally remained warmer, while areas farther away experienced cooler conditions during parts of the year. The enormous size of Pangea created a major difference between coastal regions and the interior. Areas close to the ocean received moisture carried inland by winds. These coastal places often experienced more rainfall and more moderate temperatures, because the nearby ocean helped reduce extreme heat during warmer months and reduced extreme cold during cooler months. The sea warmed and cooled more slowly than land, which helped keep nearby temperatures more stable. The interior of Pangea experienced very different conditions. Much of the land lay so far from the ocean that very little moisture reached it. Rain-bearing clouds often released their water before reaching the center of the continent. By the time air traveled deep into the interior, it had become much drier. This caused large areas to receive very little rainfall throughout the year. Many regions became deserts or dry plains where water was limited. The deserts of Pangea covered enormous areas. These deserts formed because dry air remained over much of the inland region for long periods. Without regular rainfall, rivers became less common, lakes often dried up, and vegetation struggled to survive. Sand accumulated across the land as wind carried loose particles from one place to another. Large fields of sand dunes developed in many dry regions. These dunes slowly changed shape as winds shifted over long periods. Temperatures inside these deserts often became extremely high during the daytime. Land absorbs heat quickly when the sun shines on it. Without much moisture in the air or vegetation covering the ground, temperatures rose rapidly. At night, the same dry land lost heat quickly because there were few clouds to trap warmth near the surface. This caused large differences between daytime and nighttime temperatures. Days could be very hot while nights became much cooler. The dry conditions affected every part of the landscape. Streams that formed after occasional rainfall often disappeared quickly. Water soaked into dry ground or evaporated into the atmosphere. Permanent rivers were uncommon in many inland deserts because there was not enough regular rainfall to keep them flowing throughout the year. Some rivers only carried water during certain seasons when rain temporarily increased. The lack of water influenced plant life across the dry regions. Many plants could not survive where rainfall remained scarce. Vegetation became sparse, leaving much of the soil exposed. Areas with scattered shrubs, small plants and hardy vegetation appeared where enough moisture remained to support limited growth. In the driest regions, plant life became extremely limited. Animals living in these dry environments needed ways to survive long periods without regular water. Some likely remained active during cooler parts of the day. Others may have stayed near rivers, lakes, or seasonal water sources whenever possible. Their survival depended on finding food and water within landscapes that often remained dry for extended periods. The winds crossing Pangea played an important role in shaping climate. Air constantly moved across the planet because sunlight heated different parts of Earth by different amounts. Warm air near the equator rose into the atmosphere while cooler air moved towards warmer regions to replace it. Earth's rotation also affected the direction of these winds. Together, these forces created large patterns of air movement across the globe. As winds traveled across the surrounding ocean, they picked up moisture from the water. When these moist winds reached coastal regions, clouds formed and rainfall often followed. Mountains sometimes forced the air upward, causing it to cool and release even more rain. Areas on the side of mountains facing incoming winds often received greater amounts of rainfall. After crossing mountain ranges, the air lost much of its moisture. The descending air became warmer and drier. This created broad, dry regions on the opposite side of many mountains. These rain shadow areas became even drier than surrounding regions because little moisture remained in the air after crossing the mountains. Mountain ranges across Pangea strongly influenced local climate. They redirected winds, affected rainfall patterns, and changed temperatures at different elevations. Higher elevations generally remained cooler than nearby lowlands because air temperatures decrease with height. Snow could remain on mountain peaks during colder seasons or throughout the year in some regions. Rainfall varied greatly across the supercontinent. Coastal regions near warm oceans often received regular rain. Inland deserts remained dry. Some regions experienced clear, wet and dry seasons instead of steady rainfall throughout the year. The timing of rain depended on changing wind patterns as seasons progressed. Seasonal changes became especially important because of Pangea's enormous size. During warmer months, the land heated much faster than the surrounding ocean. Warm air rose above the continent, creating areas of lower air pressure. Moist air from the ocean moved inland to replace it. As this moist air traveled across the heated land, clouds developed and heavy seasonal rainfall occurred in some regions. These seasonal wind shifts created monsoon systems over parts of Pangea. A monsoon is a seasonal change in wind direction that brings major changes in rainfall. During the warmer season, moist air flowed inland from the ocean and produced periods of heavy rain. Rivers filled with water, lakes expanded, plants grew rapidly, and many animals benefited from the temporary increase in water. When the cooler season arrived, conditions changed. The land cooled more quickly than the surrounding ocean. Cooler, heavier air developed over the continent and flowed outward toward the sea. These winds carried much less moisture because they began over dry land rather than over the ocean. Rainfall decreased greatly across many areas that had experienced wet conditions only months earlier. The change between wet and dry seasons could be dramatic in monsoon regions. During the rainy season, streams overflowed, wetlands expanded, and vegetation spread across the landscape. During the dry season, water levels dropped. Many streams became smaller, and plants experienced long periods with limited moisture. The strength of these seasonal winds depended partly on the huge size of Pangea, since such a large area of land heated strongly during warmer months. The difference in temperature between land and ocean became greater than it would have been on smaller continents. This stronger temperature difference helped create powerful seasonal wind systems capable of carrying large amounts of moisture inland. The coastline of Pangea also affected climate. The shape of bays, peninsulas, and coastal plains influenced how ocean air moved inland. Some coastlines received steady sea breezes that brought moisture and helped moderate temperatures. Other coastal regions experienced stronger seasonal changes depending on nearby wind patterns. The surrounding Panthalassa Ocean stored enormous amounts of heat. Water changes temperature more slowly than land because it requires more energy to warm and cool. This helped keep ocean temperatures more stable throughout the year. Coastal climates therefore remained less extreme than inland climates. Ocean currents also influenced global climate. Large movements of seawater carried warm water into some regions and cooler water into others. These currents affected the temperature of nearby air and influenced how much moisture entered the atmosphere. The arrangement of one giant ocean around one giant continent created current patterns that differed from those seen today. Warm ocean water increased evaporation. As water evaporated into the atmosphere, it formed water vapor. This water vapor later condensed into clouds under suitable conditions. Regions receiving moist winds from these warm waters often experienced greater rainfall. Cold ocean water reduced evaporation. Air moving across cooler waters carried less moisture than air passing over warmer waters. Coastal regions influenced by cooler currents generally received less rainfall than those exposed to warmer currents. The atmosphere itself changed over millions of years during the age of Pangea. The amount of carbon dioxide in the atmosphere varied because of volcanic activity, weathering of rocks, burial of organic material, and other natural processes. Changes in carbon dioxide affected Earth's temperature because this gas helps trap heat in the atmosphere. Periods with higher carbon dioxide levels generally allowed more heat to remain near Earth's surface. This increased average temperatures across much of the planet. Warmer conditions influenced rainfall, evaporation, and the growth of plants. Volcanic eruptions occurred during different parts of Pangea's history. Volcanoes released gases, ash, and dust into the atmosphere. Carbon dioxide released by volcanoes contributed to long-term climate changes. Ash and tiny particles sometimes reduced sunlight reaching the surface for shorter periods, causing temporary cooling in affected regions. Large volcanic provinces formed toward the later stages of Pangea's existence. Massive volcanic activity released enormous amounts of gases over long periods. Scientists believe these volcanic events influenced global temperatures, rainfall patterns, ocean chemistry, and living organisms. Cloud cover varied across different regions of the supercontinent. Coastal regions with higher humidity often experience greater cloud formation. Dry deserts usually had fewer clouds because little moisture entered the atmosphere. Fewer clouds allowed more sunlight to reach the ground during the day and allowed heat to escape more easily at night. Humidity also differed greatly across Pangea. Air near oceans contained much more water vapor than air over inland deserts. High humidity made coastal regions feel warmer because water vapor reduced the loss of heat during nighttime. Low humidity allowed deserts to cool rapidly after sunset. Seasonal temperatures depended on latitude. Areas close to the equator remained warm during most of the year because sunlight remained relatively direct. Higher latitudes experienced greater seasonal differences as the angle of sunlight changed throughout the year. Summers became warmer while winters became cooler. The length of daylight also changed with latitude. Near the equator, day and night remained close to equal throughout the year. Farther north and south, daylight lasted longer during summer and shorter during winter. These changes influenced plant growth, animal activity, and seasonal weather patterns. Large rivers flowed across some parts of Pangea where rainfall remained sufficient. These rivers transported water, sediments, and nutrients across great distances. Floodplains developed beside many rivers, creating fertile environments where plants flourished whenever enough moisture remained available. Flooding sometimes occurred during heavy seasonal rains. Rivers overflowed their banks, spreading water across nearby lowlands. Floodwaters left behind fresh layers of sediment after the water receded. These deposits supported new plant growth in many regions. Lakes formed in low areas where water collected. Some lakes remained throughout the year, while others appeared only during wet seasons. In arid regions, lakes sometimes shrank greatly or disappeared during long dry periods as evaporation exceeded incoming water. Evaporation rates remained especially high across hot inland deserts. Strong sunlight and high temperatures caused water to leave rivers, lakes, and soil rapidly. This often concentrated minerals in remaining water. When lakes eventually dried, layers of salt and other minerals remained on the ground. Many ancient rock formations from the time of Pangea contain signs of these dry environments. Thick layers of sandstone show where wind carried sand across deserts. Cracks preserved in ancient mud reveal repeated drying after wet periods. Salt deposits record places where water evaporated completely. Other rocks preserve evidence of wetter climates. Coal deposits formed where thick vegetation accumulated in wet environments over long periods. River sediments show the paths of ancient waterways. Fossils of freshwater animals reveal where rivers and lakes once existed. Plant communities differed greatly depending on local climate. Wet coastal regions supported forests with abundant vegetation. River valleys also allowed many plants to grow because water remained more available. Dry inland regions supported fewer plant species, adapted to limited rainfall. The growth of forests affected local climate in several ways. Plants released water vapor into the atmosphere through their leaves. This increased humidity and sometimes encouraged cloud formation. Forests also shaded the ground, helping reduce soil temperatures and slow water loss. Open, dry landscapes lacked these effects because vegetation remained sparse. Bare ground absorbed sunlight directly. Soil dried quickly after rainfall, and little moisture returned to the atmosphere through plants. Animals living across Pangea experienced climates that shaped their daily lives. Species living in wet forests faced different conditions than those living in deserts or seasonal plains. Migration, breeding, feeding, and shelter often depended on changing rainfall and temperature. Reptiles became especially successful in many dry environments because many possess skin that reduced water loss. Eggs protected by shells allowed reproduction away from standing water. These features helped many reptile groups spread across dry regions where amphibians found survival more difficult. Amphibians generally remained more closely tied to water because their skin lost moisture easily, and many reproduced in freshwater environments. They often lived near rivers, lakes, wetlands, or other places where water remained available for much of the year. Insects also responded to seasonal climate changes. Wet seasons provided abundant plant growth that supported large insect populations. Dry seasons reduced available food and moisture, leading many species to survive through resting stages or protected locations until wetter conditions returned. Wildfires likely occurred in some regions during dry seasons. Long periods without rainfall allowed dead plant material to accumulate and dry out. Lightning from seasonal storms could ignite these materials, causing fires that spread across dry vegetation. Such fires influenced plant communities by clearing older growth and allowing new plants to develop afterward. Dust storms were common across many desert regions. Strong winds lifted loose sand and fine soil high into the air. Dust travelled long distances before settling back onto the ground. These storms affected visibility, covered landscapes with new layers of sediment, and sometimes carried minerals into distant regions. Weather systems crossing Pangea could become very large because of the immense size of the continent. Air masses travelled long distances across land without reaching the ocean. As they moved, they changed temperature and humidity according to the surfaces below them. Dry air became even drier, while moist air gradually lost water through rainfall. Storms developed where warm, moist air met cooler air. Rising air produced clouds, rain, and sometimes powerful winds. Seasonal heating increased the energy available for storm development, particularly in regions influenced by monsoon circulation. Thunderstorms likely formed frequently during warmer seasons in areas receiving moist air from nearby oceans. These storms produced heavy rain, lightning, and strong winds. Rainfall often fell rapidly over short periods, filling streams and rivers quickly. The absence of nearby oceans across much of the interior limited the formation of regular rainstorms. Without enough moisture, clouds remained scarce over many inland areas. Long periods passed with little or no rainfall. Earth's rotation continued to influence atmospheric circulation during the age of Pangea. Rotating motion affected the direction of winds and helped establish large climate belts around the planet. These circulation patterns interacted with the shape of the supercontinent, creating regional climate differences. Polar regions during parts of Pangea's history experienced cooler climates than tropical regions. Some southern areas preserved evidence of ancient glaciers before Pangea reached its later stages. These glaciers slowly moved across the land, leaving marks on rocks and carrying sediments. As climate changed through time, many glaciers disappeared as warmer conditions spread across large parts of the planet. Ice retreated toward higher latitudes and higher elevations. The reduction of widespread ice influenced sea levels, river systems, and ecosystems. Sea levels changed during different periods because of movements of Earth's crust, changes in ocean basins, and the amount of water stored as ice. Rising seas flooded some coastal regions while falling seas exposed additional land. These changes affected coastlines and local climates. Shallow seas occasionally spread across low parts of the continent. These inland seas influenced nearby weather by increasing humidity and moderating temperatures. Marine life expanded into these waters whenever connections with larger oceans remained open. Chemical weathering of rocks occurred more rapidly in warm, wet climates, because water and higher temperatures increased the breakdown of minerals. Dry deserts experienced slower chemical weathering, but often showed greater physical breakdown, as daily temperature changes caused rocks to crack and break apart. Rivers carried sediments from mountains into valleys, lakes, and coastal regions. These sediments recorded changing climate conditions over millions of years. Thick layers of sand often indicated dry environments, while mud and plant remains pointed to wetter conditions. Scientists study these rock layers to understand Pangea's climate. Ancient soils preserve signs of rainfall, temperature, and vegetation. Fossils reveal which plants and animals lived under particular climate conditions. Mineral deposits also provide clues about evaporation, rainfall, and seasonal changes. Tree fossils sometimes preserve growth rings that formed during alternating growing and resting seasons. Wider rings may indicate years with favorable growing conditions, while narrower rings suggest more difficult conditions. These records help scientists estimate seasonal climate patterns in ancient forests. Pollen grains preserved in sediment reveal the types of plants growing in different regions. Since different plants prefer different climates, pollen helps scientists reconstruct ancient rainfall and temperature patterns across Pangea. The distribution of fossils across the supercontinent also reflects climate zones. Similar plant and animal species often occupied regions with similar climates, even when separated by great distances across the giant continent. Differences in fossil communities reveal changes in rainfall, temperature, and seasonal conditions. Climate during the age of Pangea did not remain exactly the same throughout its existence. Over millions of years, Earth's continents shifted slowly because of plate movement. Mountain ranges rose and eroded. Volcanic activity increased or decreased. Atmospheric gases changed. Ocean circulation evolved. Each of these factors gradually altered climate patterns across the supercontinent. As the continents slowly began to separate during the later part of Pangea's history, new coastlines formed. Oceans entered areas that had previously been far inland. Moisture reached regions that had long remained dry. Wind patterns gradually adjusted to the changing arrangement of land and sea. The breakup of the supercontinent slowly reduced the enormous inland deserts because no place remained as far from the ocean as before. Coastal climates expanded as new shorelines developed. Rainfall patterns shifted and monsoon systems gradually changed in strength and location. The climate of Pangea remains one of the most important subjects in the study of Earth's ancient history, because it affected landscapes, rivers, forests, deserts, animals, plants, weather systems, and the long-term development of life across the supercontinent over millions of years. Life in the oceans around Pangea was rich, active, and filled with many different forms of life that lived in waters of many depths and temperatures. While the land of Pangea was joined together into one giant supercontinent, the seas around it covered huge parts of Earth. These waters supported countless living things, from tiny drifting organisms to enormous marine reptiles that hunted across wide stretches of ocean. Every level of the sea contained life. The surface waters, the middle depths, the deep ocean floor, shallow coastal areas, warm reefs, muddy bottoms, rocky shores, and open waters each provided places where different animals and plants could survive. These living communities changed over long periods as Earth's climate shifted. Sea levels rose and fell, continents slowly moved, and different groups of animals appeared, spread, and disappeared. The largest ocean surrounding Pangea was known as Panthalassa. It covered most of Earth's surface and was much larger than any ocean that exists today. Around the edges of Pangea were smaller seas and coastal waters where many marine animals found food and safe places to grow. Warm sunlight reached shallow waters, allowing many tiny living organisms to produce food through photosynthesis. These tiny forms of life became the foundation of the food chain. Very small floating plants and algae drifted through the water using sunlight to make food. Tiny animals fed on these floating plants. Small fish and other sea creatures then fed on the tiny animals. Larger fish hunted the smaller fish, while sharks and marine reptiles hunted many of these larger animals. At the very top of the food chain lived the biggest hunters of the seas. The oceans around Pangea contained countless microscopic forms of life that could not be seen without strong magnification. Although these organisms were tiny, they were among the most important living things in the sea. They floated freely with ocean currents and multiplied in enormous numbers. Many kinds of plankton existed, including tiny algae and single-celled organisms. These organisms formed the first source of food for many sea animals. Their bodies also helped store carbon, and when they died, many settled to the sea floor. Over very long periods, these remains became part of thick layers of sediment that slowly hardened into rock. Many kinds of algae also lived in the oceans. Some floated freely while others grew attached to rocks, shells and reefs. Green algae, red algae and other early forms covered shallow coastal waters where sunlight easily reached the sea floor. These plants provided food for many animals and created places where small sea creatures could hide from hunters. Areas rich in algae often supported large numbers of fish, shellfish, worms, and other small animals. Sponges were among the oldest animals living in the seas around Pangea. They remained attached to rocks and the sea floor throughout their lives. Water constantly flowed through their bodies as they filtered tiny food particles from the sea. Their simple body structure allowed them to survive in many different marine environments. Some sponges formed colourful patches across rocky bottoms, while others grew into larger shapes that provided shelter for small sea animals seeking protection. Corals were another important part of shallow marine ecosystems. Ancient corals formed reefs that stretched across warm coastal waters. These reefs became crowded homes for many different species. Small fish swam between the coral branches. Crabs searched for food among the rocky spaces. Sea snails slowly moved across the reef surfaces. Worms burrowed into small openings. Many shell-covered animals attached themselves to hard surfaces. Coral reefs became centers of marine life because they offered food, shelter, breeding areas, and protection from larger hunters. The sea floor around these reefs contained many different kinds of shellfish. Clams buried themselves beneath soft sand and mud while filtering food from the water. Brachiopods covered parts of the sea floor in huge numbers. These shell-bearing animals had existed for a very long time before the age of Pangea and remained common in many marine environments. Although they looked somewhat like clams, they belonged to a different group of animals. Many species attached themselves to rocks using strong stalks, while others rested freely on the bottom. Crinoids also covered parts of the sea floor. These animals belong to the same larger group as modern sea stars and sea urchins. Many crinoids were attached to the bottom by long stems that lifted their feeding arms into flowing water. Their feather-like arms captured tiny food particles carried by ocean currents. Large fields of crinoids sometimes covered wide areas of the sea floor, creating underwater habitats where other small animals lived among their stems. Sea lilies, which were another name often used for many crinoids, created beautiful underwater scenes. Although they looked like underwater plants, they were animals. Small fish swam around them, while tiny shellfish hid beneath their stems. Dead crinoids added large amounts of broken, skeletal material to the sea floor, eventually contributing to the formation of certain kinds of limestone over very long periods. Sea stars moved slowly across the ocean floor searching for food. They fed on shellfish, worms, and many other animals. Their flexible tube feet helped them crawl over rocks and sand. Sea urchins also lived across many marine environments. Their round bodies were covered with movable spines that helped protect them from hunters. They fed on algae and other small food sources found on the sea floor. Many different kinds of worms lived beneath the ocean floor. Some dug tunnels through soft mud while feeding on organic material buried in the sediment. Others lived inside tubes that they built from sand grains or secreted materials. These worms constantly mixed the sediments as they moved, helping recycle nutrients within marine ecosystems. Their tunnels allowed oxygen-rich water to reach deeper layers of the sea floor, supporting other forms of life. Trilobites had already lived in Earth's oceans for an extremely long time before the age of Pangea. These hard-shelled animals were among the most successful groups in ancient marine history. They had segmented bodies, compound eyes, and many pairs of legs beneath their shells. Different species occupied different environments. Some crawled across the sea floor, searching for food. Others swam through the water for short distances. Some fed on dead organic material, while others hunted smaller animals. During the time of Pangea, however, trilobites were no longer as diverse as they had once been. Many earlier groups had already disappeared before the supercontinent reached its greatest size. Only a few kinds remained. These surviving trilobites continued living mainly on the sea floor, where they searched for food among mud, sand and rocks. Their strong shells protected them from many hunters, although large fish and marine reptiles could still capture them. Eventually, the Great Extinction near the end of the Permian period caused the final disappearance of trilobites from Earth after they had survived for hundreds of millions of years. Ammonites became one of the best-known animals of the seas around Pangea. These relatives of modern squid and octopuses lived inside tightly coiled shells, divided into many internal chambers. As the ammonite grew, it built larger chambers while sealing off the older ones. Gas and liquid inside these chambers helped control buoyancy, allowing the animal to rise or sink in the water with less effort. Many different kinds of ammonites existed. Some had smooth shells, while others had strong ribs, bumps, or spines. Their shell sizes varied greatly. Smaller species could fit inside a person's hand, while larger species reached much greater sizes. Their soft bodies extended from the shell opening, with several arms surrounding a sharp beak used to catch prey. Large eyes helped them detect food and avoid hunters. Ammonites fed on small fish, tiny shellfish, worms, and other marine animals. Some may have hunted actively, while others likely captured slower-moving prey. They themselves became important food for sharks, marine reptiles, and larger fish. Because ammonites reproduced quickly and evolved into many different forms, their fossils help scientists identify the ages of ancient rocks found across many parts of the world. Another shell-bearing relative of squid, called the nautiloid, also lived in these seas. Nautiloids had existed long before ammonites and survived through many periods of Earth's history. Some species had straight shells, while others had curved or coiled shells. Modern nautiluses are distant relatives of these ancient animals. Nautiloids moved through the water using jet propulsion, by forcing water from a body opening, allowing them to travel while searching for food. Fish were extremely diverse during the age of Pangea. Countless species occupied every marine environment. Some remained close to reefs, others preferred open waters, while many stayed near the seafloor. Fish varied greatly in size, shape, feeding habits, and swimming ability. Small fish often travel together in large groups, reducing the chance that hunters would catch any single individual. Larger fish usually hunted alone or in much smaller groups. Ray-finned fish became increasingly important during this time. Their fins were supported by flexible rays that allowed smooth movement through the water. These fish developed many different body shapes suited for different habitats. Some had flattened bodies for life near the sea floor. Others developed streamlined shapes for fast swimming in open water. Their diets also differed greatly. Some ate tiny drifting organisms, others fed on algae, shellfish, worms, or smaller fish. Lobe-finned fish continued to exist as well. These fish had strong, fleshy fins containing bones that were important in the distant history of vertebrate evolution. Although many earlier groups had already disappeared, some lobe-finned fish survived in marine and freshwater environments. Their strong fins allowed them to move differently from ray-finned fish. Cartilaginous fish also flourished in the oceans around Pangea. Their skeletons were made mostly of cartilage instead of bone. Sharks belonged to this group along with rays and their relatives. Cartilage made their bodies lighter while still providing strength and flexibility. Sharks became some of the most successful hunters in ancient oceans because of their excellent senses, powerful jaws, and efficient swimming ability. Many shark species lived during this period. Some were small and fed mainly on shellfish or tiny animals living near the sea floor. Others hunted fish in open water. Large sharks searched for bigger prey, including marine reptiles, large fish, and ammonites. Different shark species occupied different parts of the oceans, reducing direct competition for food. Sharks possessed rows of replaceable teeth. When one tooth became damaged or fell out, another moved forward to take its place. This allowed sharks to continue hunting effectively throughout their lives. Their highly developed sense of smell helped detect injured animals from long distances. Sensitive organs in their heads allowed them to detect weak electrical signals produced by the muscles of nearby animals, making hidden prey easier to locate. Some sharks had broad crushing teeth designed for breaking shells. These species fed on clams, brachiopods, crabs, and other hard-shelled animals. Other sharks had long pointed teeth that were better suited for catching slippery fish. Each type of tooth reflected the feeding habits of the species. Marine reptiles became some of the most impressive animals living in the oceans around Pangea. Although they spent most of their lives in the sea, they still needed to breathe air because they were reptiles. Many had streamlined bodies, strong swimming tails, paddle-like limbs, and powerful muscles that allowed them to travel long distances through open water. Some of the earliest marine reptiles appeared during the Permian period, while many more groups became common during the Triassic period after the Great Extinction. Early marine reptiles explored many ecological roles as the oceans gradually recovered. Different groups developed different body shapes suited for their feeding habits and swimming styles. Ichthyosaurs became one of the best-known marine reptiles after the beginning of the Triassic period. Their bodies were well suited for life in open water. They possessed long snouts filled with sharp teeth, large eyes that provided excellent vision, and strong tails for swimming. Many species hunted fish and squid-like animals. Some grew to very large sizes, while others remained much smaller. Ichthyosaurs gave birth to live young instead of laying eggs on land. Fossils showing unborn young inside adult females have provided direct evidence of this reproductive method. Giving birth in the water allowed these reptiles to spend their entire lives at sea without returning to beaches. Nothosaurs lived mainly in shallow coastal waters. They had long necks, sharp teeth, and webbed feet adapted for swimming. Although capable swimmers, they may have rested on land from time to time. They hunted fish and other marine animals near coastlines and shallow seas. Placodonts developed broad crushing teeth for feeding on shellfish. Their heavy bodies and strong jaws allowed them to crack open hard shells. Some species developed wide, flat bodies suited for feeding along the sea floor. Others evolved protective armor that covered much of their backs. Later, during the Triassic period, plesiosaurs began appearing. Some had very long necks and relatively small heads, allowing them to catch fish and other prey with quick movements. Other plesiosaurs eventually developed shorter necks and larger heads with stronger jaws. These reptiles became important hunters in marine ecosystems during later periods. Marine reptiles occupied many different levels of the food chain. Smaller species fed on fish, squid-like animals, shellfish, and crustaceans. Larger species hunted other marine reptiles, sharks, and large fish. Young reptiles faced danger from many hunters until they grew large enough to defend themselves. Crustaceans were common throughout the seas surrounding Pangea. Ancient relatives of modern crabs, shrimp, and lobsters searched for food among rocks, reefs, and muddy bottoms. Many fed on dead animals or organic material lying on the sea floor. Others hunted worms and smaller invertebrates. Their hard outer coverings protected them from many dangers, although they remained important food for larger hunters. Sea snails moved slowly across rocks, reefs, and sandy bottoms. Some grazed on algae growing over hard surfaces. Others drilled holes through shells to feed on animals inside. Different shell shapes reflected different ways of life. Thick shells provided protection, while smooth, streamlined shells allowed easier movement through sand. Many bivalves filled coastal waters. Oysters, clams, and similar animals filtered enormous amounts of water each day, removing tiny food particles. Their feeding activity helped keep coastal waters cleaner while transferring nutrients through marine food chains. Squid-like animals without external shells also swam through these ancient oceans. Their soft bodies allowed rapid movement. Using jet propulsion, they could quickly escape hunters or chase prey. Their large eyes provided sharp vision, and their arms helped capture fish and smaller animals. Ocean currents strongly influenced life around Pangea. These moving masses of water carried nutrients from deep areas toward the surface, supporting rich growth of plankton. Currents also transported tiny young animals and drifting eggs across great distances. Many marine species spread into new areas through these natural movements of seawater. Water temperature varied greatly depending on location. Tropical coastal waters remained warm throughout much of the year and supported abundant marine life. Cooler waters farther from the equator contained different communities adapted to lower temperatures. Deep ocean waters stayed much colder than surface waters because sunlight could not warm them directly. Changes in sea level greatly affected marine ecosystems. When sea levels rose, shallow coastal habitats expanded, creating new homes for many species. Coral reefs spread into newly flooded regions. Fish entered fresh coastal waters rich in food. Shellfish colonized new seafloors. When sea levels later fell, many shallow habitats disappeared, forcing marine animals to move into remaining suitable environments. Storms also influenced life in the oceans around Pangea. Strong waves stirred sediments from the sea floor, buried some animals beneath mud, and broke apart reefs. At the same time, storms mixed ocean waters, bringing oxygen and nutrients into different layers. After storms passed, marine communities gradually recovered and continued growing. The sea floor itself displayed many different environments. Rocky bottoms supported attached organisms such as sponges, corals, and brachiopods. Sandy areas contained burrowing clams and worms. muddy bottoms held countless small animals, feeding on organic material that settled from above. Deep ocean floors received a slow but constant rain of dead plankton and other organic remains from surface waters. Many marine animals depended on camouflage to survive. Their body colours matched surrounding rocks, sand or open water. Some shell patterns helped break up their outlines, making them more difficult for hunters to detect. Others buried themselves beneath sediments, leaving only small openings for breathing or feeding. Reproduction occurred in many different ways. Many shellfish released eggs and sperm directly into the water, where fertilization took place. Huge numbers of eggs increased the chance that some young would survive, despite many being eaten. Fish displayed many reproductive methods. Some scattered eggs over plants or rocks, while others guarded nests or protected developing young for a time. Marine reptiles often produced fewer young but invested more care in their offspring through live birth or carefully chosen nesting sites for egg-laying species. Young marine animals usually faced greater dangers than adults. Tiny fish became food for larger fish. Small ammonites were hunted by many predators. Newly hatched reptiles risked attacks from sharks and other marine hunters. Only a small number survived to adulthood, yet those survivors maintained healthy populations across the oceans. Many animals migrated through different marine environments during various stages of life. Young fish often remained in protected shallow waters before moving into deeper seas as adults. Some sharks used coastal nurseries, where young individuals found greater safety. Seasonal changes in water temperature and food supplies also encouraged movement between regions. Near the end of the time when the giant supercontinent called Pangea covered much of Earth's land, a new group of reptiles began to appear. These early dinosaurs did not become the rulers of the land as soon as they appeared. Their first steps were quiet and slow. They lived beside many other kinds of animals that had already spread across forests, river valleys, dry plains, and open land. At first they formed only a small part of the living world. Their bodies, behavior, and way of life slowly changed over many millions of years as they adapted to the changing conditions around them. The first dinosaurs appeared during the late Triassic period, around 230 million years ago. At that time, Earth looked very different from the planet seen today. Most of the land was joined together into one huge continent called Pangea. Around this giant landmass stretched a vast ocean known as Panthalassa. The inside of Pangea was often dry because much of it lay far from the sea. Rain did not reach many inland places very often. Long dry seasons covered large areas, while heavy rain sometimes came during other parts of the year. Rivers changed their paths, lakes formed and disappeared, and many plants and animals had to survive difficult conditions. The climate during this time placed pressure on many living things. Animals needed to find food and water even when conditions became harsh. Only those that could survive changing weather, dry land, and shifting food supplies continued to live and reproduce. These challenges helped shape the bodies and behavior of many animals, including the earliest dinosaurs. Long before dinosaurs appeared, reptiles had already become successful across much of the land. They had developed eggs with protective shells that could be laid on land instead of in water. Their skin reduced water loss, allowing them to live in places where water was not always easy to find. Over time, reptiles spread into many different forms. Some stayed small, while others grew very large. Some became meat-eaters, while others fed on plants. Among these reptiles were a group known as archosaurs. This group included the ancestors of dinosaurs, crocodiles, and flying reptiles called pterosaurs. Archosaurs developed several body features that helped them move well on land. Their legs stood more directly beneath their bodies than the legs of many earlier reptiles. This body shape made walking and running more efficient. Strong muscles supported their movement and helped them travel longer distances while using less energy. The earliest dinosaurs came from one branch of the Archosaur family. Scientists continue to study fossils to understand exactly how these early dinosaurs developed. Every new fossil provides fresh information about their appearance, growth, movement, and daily lives. Even though many questions remain, fossil discoveries from different parts of the world have helped build a clearer picture of their early history. The oldest known dinosaur fossils have been found mainly in parts of South America. During the late Triassic period, South America was joined directly to Africa and the other continents because they were all part of Pangea. Animals could travel across large areas without crossing wide oceans. This allowed many kinds of animals to spread into different regions as they searched for food, mates, and better places to live. One of the earliest known dinosaurs was Eoraptor. It lived about 231 million years ago in what is now Argentina. Eoraptor was small, measuring only about the length of a medium-sized dog. It walked on two legs and had a light body that allowed it to move quickly. Its hands could grasp objects, and its sharp teeth suggest that it probably ate small animals, insects, and perhaps some plants as well. Scientists believe it had a flexible diet that allowed it to survive in changing environments. Another early dinosaur was Herrerasaurus, which also lived in what is now Argentina. It was much larger than Eoraptor and had powerful legs, strong jaws, and sharp teeth. Herrerasaurus hunted other animals and likely stood near the top of the local food chain in some places. Although it was larger than many early dinosaurs, it still shared the land with many other reptiles that competed for food. Styracosaurus lived in what is now Brazil during the same general period. Like several other early dinosaurs, it walked on two strong legs and had a long tail that helped keep its body balanced while moving. It probably hunted small animals and could move quickly when chasing prey. Fossils of Styracosaurus have helped scientists understand how the earliest meat-eating dinosaurs were built. These first dinosaurs were generally much smaller than the giant dinosaurs that appeared much later. Most had long legs, long tails, light bones, and narrow bodies. Their small size may have helped them move through forests, along riverbanks, and across open ground with greater ease. Quick movement allowed them to escape larger predators, search for food, and explore new areas. Their feet were built for active movement. Many had three main toes that carried most of their weight while walking or running. Their legs were positioned beneath their bodies instead of spreading outward. This body design allowed more efficient movement than many other reptiles living at the same time. Efficient movement meant they could travel greater distances while using less energy. The earliest dinosaurs probably laid eggs in nests built on the ground. Like modern reptiles and birds, they reproduced by laying eggs with protective shells. Fossil discoveries from later dinosaur species show nests, eggs, and even groups of young dinosaurs. Although direct evidence from the very earliest dinosaurs remains limited, scientists believe many of their breeding habits were similar. During this time, Earth contained many animals besides dinosaurs. Large amphibians still lived in rivers and lakes. Ancient crocodile relatives walked across the land. Armored reptiles browsed on plants. Fast meat-eating reptiles hunted across open areas. Flying reptiles moved through the skies, searching for fish and small animals. Dinosaurs formed only one part of this rich collection of life. Many early reptiles competed for the same food sources. Meat-eaters searched for small animals, while plant-eaters depended on ferns, seed ferns, cycads, horsetails, and early conifer trees. Food supplies changed as seasons became wetter or drier. Animals constantly adapted their behavior to survive. Plants played an important part in the rise of dinosaurs. Forests provided shelter from larger predators and protected smaller animals from harsh sunlight. Thick vegetation offered places to hide while hunting or escaping danger. Plant life also supported insects and other small creatures that became food for early meat-eating dinosaurs. The rivers flowing across Pangea supported many forms of life. Fish filled lakes and streams. Small reptiles hunted near the water. Larger predators often waited near riverbanks where animals gathered to drink. During dry seasons, water became even more important because many animals depended on the remaining rivers and lakes for survival. The changing environment created opportunities for animals that could adjust quickly. Dinosaurs possessed several features that helped them respond to these challenges. Their upright posture allowed steady movement across long distances. Their active lifestyle enabled them to search widely for food. Their flexible diets in some species allowed them to eat different kinds of food when supplies changed. Scientists believe that early dinosaurs may have grown faster than many reptiles living beside them. Faster growth meant young dinosaurs reached adult size more quickly. This reduced the time they remained small and vulnerable to predators. Bones from some early dinosaur fossils contain tiny growth structures that provide clues about how rapidly they developed. Another important feature may have been their breathing system. Evidence from fossil bones suggests that dinosaurs developed an efficient way of moving air through their bodies. This allowed them to stay active for longer periods. Modern birds, which descended from certain dinosaurs, possess highly efficient breathing systems. Scientists continue studying fossils to understand when this feature first appeared. The late Triassic world did not remain stable. Powerful volcanic activity affected many regions as Pangea slowly began to break apart. Cracks formed within the giant continent. Molten rock rose through these openings and produced enormous volcanic eruptions over long periods. These eruptions released huge amounts of gases into the atmosphere. The gases changed Earth's climate. Temperatures shifted, rainfall patterns changed, and many environments became unstable. Forests expanded in some places and disappeared in others. Rivers changed course, lakes dried up, and new habitats formed. Plants and animals faced increasing pressure as their surroundings continued changing. Many groups of reptiles that had dominated the land for millions of years struggled during these environmental changes. Some species disappeared completely. Others experienced large declines in their numbers. Scientists believe that a major extinction event occurred near the end of the Triassic period, around 201 million years ago. This event removed many of the reptiles that had competed directly with dinosaurs. As many competing animals disappeared, dinosaurs found more opportunities to spread into empty habitats. They expanded into forests, river valleys, floodplains, and other environments that had become available. Different dinosaur groups began developing specialized bodies suited for different ways of life. Some early dinosaurs remained meat-eaters. Others developed bodies suited for feeding on plants. Plant-eating dinosaurs gradually developed stronger jaws, different teeth, and larger digestive systems that allowed them to process tough vegetation. Meat-eating dinosaurs refined their hunting abilities through stronger legs, sharper claws, and improved balance. The splitting of Pangea also played an important part in dinosaur history. As the giant continent slowly separated into smaller landmasses, populations of dinosaurs became isolated from one another. Over many millions of years, isolated groups changed in different ways. New species developed as each population adapted to its own environment. food sources, and climate. Molten rock beneath the surface of the supercontinent remained active throughout the time when Pangea existed. Deep below the ground, the inside of Earth contained very hot rock that stayed under great pressure. This heat came from the planet's formation and from the slow breakdown of natural radioactive materials inside the crust and mantle. Even though the surface often appeared solid and stable, the rocks far below were slowly moving. These movements created stress that built up over very long periods. As the pressure increased, the crust cracked, shifted, and bent. These changes caused earthquakes, volcanic eruptions, mountain building, and many other geological events that continuously changed the land across the supercontinent. The crust of Earth was divided into large pieces known as tectonic plates. These plates rested on a layer of hot rock that could slowly flow over long periods. The movement was extremely slow, often only a few centimeters each year. But over millions of years, these small movements changed the shape of continents and oceans. During the time of Pangea, many of these plates had joined together to form one enormous landmass. Even after they came together, the plates never stopped moving. Their steady movement created stress throughout the supercontinent. Rocks were pushed together in some places, while they were pulled apart in others. The pressure affected the landscape in many different ways. Large mountain ranges formed where parts of the crust were forced together. Rocks that had once rested deep below the surface were slowly lifted higher as the crust folded and broke. Some rocks cracked into large blocks that moved upward while others moved downward. This created steep slopes, valleys, cliffs, and high peaks. Wind and rain slowly wore these mountains down, carrying broken pieces into rivers and lakes. At the same time, fresh movements beneath the ground continued lifting parts of the mountains higher. This steady cycle of uplift and erosion changed the appearance of the land again and again. Earthquakes happened whenever built-up pressure inside the crust became too great for the rocks to hold. Instead of bending forever, the rocks suddenly broke or slipped along cracks called faults. The energy that had been stored inside the rocks was released in a very short time. This energy traveled through the ground as seismic waves. The shaking could be weak or extremely strong, depending on the amount of energy released and the distance from the fault. Some earthquakes lasted only a few moments, while others continued for much longer. After a major earthquake, smaller earthquakes often followed as the rocks slowly settled into new positions. Faults spread across many parts of the supercontinent. Some faults stretched for hundreds of kilometers. Different kinds of faults formed depending on how the rocks moved. In some places, one side of the crust moved upward. In other places, one side dropped lower. There were also faults where two blocks of crust slid sideways past each other. Every movement changed the shape of the land. Valleys formed where blocks sank, while hills and ridges formed where blocks rose higher. Many earthquakes happened far below the surface, where people and animals could not see them directly. The shaking reached the surface and affected forests, rivers, lakes, and open plains. Loose rocks rolled down hillsides. Cracks opened across the ground. Some lakes changed shape when nearby land shifted. Rivers sometimes found new paths after earthquakes lifted or lowered parts of the landscape. Wet ground could lose its strength during severe shaking, causing soil to move like a thick liquid. Trees growing in these areas could fall over as the ground beneath them changed. Animals living during the age of Pangea faced these natural events without warning. They could not predict when the ground would shake. Some may have sensed small changes before earthquakes through vibrations or sounds that humans cannot easily notice today. Burrowing animals sometimes left their tunnels before major shaking. other animals moved away from areas where unusual activity disturbed the ground. These reactions may have improved the chances of survival for some species, although many animals still suffered during powerful geological events. Volcanoes formed where molten rock reached the surface through cracks in the crust. This molten rock, called magma, while underground, became lava after flowing onto the surface. Volcanoes varied greatly in size and shape. Some grew into broad mountains with gentle slopes, while others formed steep cones built from layers of ash and hardened lava. Every eruption added new material around the volcanic opening. Over long periods, repeated eruptions created massive volcanic landscapes across parts of the supercontinent. Not every volcanic eruption happened in the same way. Some eruptions were gentle, allowing lava to flow slowly across the ground. These lava flows spread over great distances before cooling into solid rock. Other eruptions were violent, because gases trapped inside the magma expanded rapidly as pressure decreased. These eruptions blasted ash, broken rock, and hot gases high into the air. Thick clouds of volcanic ash spread across wide areas before settling back onto the ground. Volcanic ash played an important role in changing the land. Fresh ash covered forests, rivers, lakes, and open plains. Thick layers buried plants and animals. Smaller amounts mixed with soil and later became rich sources of minerals that supported new plant growth. Rain washed ash into rivers where it settled as layers of fine sediment. These layers later hardened into sedimentary rock. Scientists today study these rocks to learn about ancient volcanic activity. Lava flowing across the land destroyed everything in its direct path. Trees burned or were buried beneath thick rock. Streams became blocked, forcing water to find new routes. Lakes sometimes formed behind natural dams, created by hardened lava. Over thousands of years, these lakes filled with sediment or overflowed into surrounding valleys. The landscape changed with every eruption as fresh rock covered older surfaces. Some volcanic eruptions released enormous amounts of gas into the atmosphere. Water vapor, carbon dioxide, sulfur dioxide, and other gases escaped from the molten rock. Water vapor added moisture to the air. Carbon dioxide became part of Earth's natural carbon cycle. Sulfur dioxide combined with water in the atmosphere to form tiny droplets that reflected some sunlight. Large volcanic eruptions sometimes affected climate for years by reducing the amount of sunlight reaching Earth's surface. Cooler temperatures could influence plant growth and the lives of animals across wide regions. The inside of Earth constantly supplied heat that kept geological activity alive. Heat moved slowly upward from the deep interior. Hot rock beneath the crust rose while cooler rock slowly sank. This movement, called mantle convection, acted over millions of years and helped move tectonic plates across the planet. Although these movements were slow, they never completely stopped. They continued changing the position of continents, oceans, mountains, and volcanoes throughout the existence of Pangea. Some volcanic regions remained active for extremely long periods. New eruptions happened again and again from the same volcanic systems. Layers of lava built up until they reached great thickness. Each layer recorded another stage in the geological history of the region. Later erosion exposed these layers, allowing scientists to study the sequence of eruptions that happened over millions of years. Cracks sometimes opened in the crust without immediately forming large volcanoes. These long fractures allowed lava to pour onto the surface through many openings instead of one central vent. Huge lava fields formed as molten rock spread across enormous areas. Layer after layer covered older rocks until thick volcanic plateaus developed. These events changed large sections of the supercontinent and influenced local environments for very long periods. The movement of molten rock beneath the crust also caused the ground to rise before eruptions. As magma collected underground, it pushed the overlying rocks upward. Small earthquakes often happened during this process because the rocks cracked, while the magma forced its way through them. If enough pressure built up, the magma finally reached the surface. In other cases, the magma cooled underground before erupting, forming large bodies of solid rock hidden beneath the surface. Underground magma that cooled slowly formed rocks with large mineral crystals, because the cooling process took a long time. Magma that reached the surface cooled much more quickly, producing rocks with much smaller crystals. These different cooling rates created many kinds of igneous rocks that remain important evidence of ancient geological activity. Scientists examine these rocks today to understand the temperatures, pressures, and conditions that existed during their formation. Hot water circulated through cracks near volcanic regions. As groundwater moved close to hot rocks, it became heated before rising back toward the surface. This created hot springs and sometimes powerful geysers, where underground conditions allowed pressure to build. Minerals dissolved in the hot water were deposited as the water cooled, forming colorful mineral layers around springs and inside underground cracks. These mineral deposits became valuable parts of Earth's geological record. Some volcanoes collapsed after major eruptions emptied large underground magma chambers. Without enough support below, the ground above sank inward, creating large circular depressions called calderas. These features sometimes filled with water to form lakes. New volcanic activity occasionally returned inside older calderas, creating fresh volcanic cones within the larger depression. Geological activity often continued long after the first major eruption had ended. Earthquakes and volcanoes often happened in connected regions because both resulted from the movement of tectonic plates. Areas where plates collided, separated, or slid past each other experienced frequent geological activity. The forces beneath the supercontinent remained active through millions of years, changing landscapes little by little as well as through sudden, powerful events. The supercontinent remained joined for a very long period, but the Earth beneath it never stopped changing. Deep below the surface, the planet continued to produce heat from its hot interior. This heat slowly moved through the mantle, which is the thick layer of hot rock located between the Earth's crust and its core. Although the mantle is made of solid rock, the rock can slowly flow over very long periods because of the intense heat and pressure. This slow movement carried energy upward and created forces that acted on the base of the Earth's crust. These forces were present throughout the time that Pangea existed and gradually became strong enough to affect the stability of the giant landmass. The Earth's outer shell is divided into large pieces called tectonic plates. These plates include both continents and ocean floors. They are always moving, but the movement is extremely slow. Most plates move only a few centimeters each year. Even though this movement is slow, it continues without stopping for millions of years. As time passes, these small yearly movements produce major changes in the positions of continents and oceans. Pangea itself was formed because tectonic plates moved toward one another over many millions of years. The same forces that created the supercontinent later caused it to split apart. When Pangea existed, almost all of Earth's major land areas were joined into one enormous continent. This created a very thick section of continental crust. Continental crust is lighter than the rock beneath it, so it floats on the mantle. However, when so much continental crust gathered together in one place, it changed the way heat moved beneath the surface. The thick crust acted like a covering that slowed the escape of heat from the Earth's interior. As heat collected beneath Pangea, pressure slowly increased below the supercontinent. Scientists believe that rising heat beneath Pangea played an important part in starting the breakup. Hot material from the mantle slowly moved upward beneath the giant landmass. This upward movement is often linked to mantle convection. Convection happens when hotter material rises while cooler material sinks. These slow-moving currents transport heat through the mantle. As rising currents reach the underside of Pangea, they push gently against the crust above them. This pressure slowly weakened parts of the supercontinent. The rising heat did not break the continent apart in a short time. Instead, the process lasted for many millions of years. The crust first stretched very slowly. As it stretched, small cracks appeared. These cracks became longer and deeper over time. The stretching continued because the forces beneath the continent did not stop. Eventually, the cracks developed into long valleys known as rift valleys. These valleys marked the places where the continent was beginning to separate. A rift forms when the Earth's crust is pulled apart. During this process, the crust becomes thinner. Large blocks of land slowly move downward between faults, creating long depressions in the landscape. Volcanoes often appear in these regions because hot material from below can reach the surface more easily through the weakened crust. Earthquakes also become common because the rocks are under stress as they break and move. Many scientists believe that the first major stage of Pangea's breakup began around 201 million years ago. At this time, stretching became stronger across parts of the supercontinent. Large cracks developed between areas that would later become separate continents. These early rifts did not immediately produce new oceans. Instead, they marked the beginning of a very long process that continued over tens of millions of years. Mantle plumes may also have helped weaken the supercontinent. A mantle plume is a rising column of unusually hot rock from deep within the mantle. As the hot material rises, it brings extra heat toward the base of the crust. This additional heat can soften rocks and make them easier to stretch and break. If a mantle plume reaches the underside of a continent, it may cause the land above it to rise slightly before cracking begins. This lifting places additional stress on the crust. Some researchers connect the breakup of Pangea with one or more large mantle plumes that developed beneath the supercontinent. These plumes could have heated broad regions of the crust, making them weaker than before. Once the crust weakened, tectonic forces pulling in different directions became more effective at creating large rifts. The combined action of mantle heat and plate movement gradually separated the land. The movement of tectonic plates is driven by several different processes. One important process is called slab pull. This happens when old oceanic crust becomes colder and heavier as it moves away from ocean ridges. Eventually, the heavy crust sinks into the mantle at deep ocean trenches. As it sinks, it pulls the rest of the tectonic plate with it. This pulling force influences the movement of continents that are attached to the same plate. Another important process is called ridge push. New oceanic crust forms at mid-ocean ridges, where magma rises from the mantle and cools into solid rock. The newly formed crust is warm and stands higher than older ocean floors. Gravity causes the new crust to slide slowly away from the ridge. This movement pushes the tectonic plates apart. Ridge push and slab pull work together with mantle convection to keep the plates moving. As Pangea remained joined, these forces continued acting on different parts of the Earth's surface. Eventually, the balance of forces changed. Instead of moving toward one another, some plates began moving away from each other. This change caused the supercontinent to stretch. Areas that experienced the greatest stretching became the first places where splitting occurred. The crust does not break evenly across an entire continent. Certain regions are weaker than others because of differences in rock type, earlier faults, or previous mountain building events. These weaker zones become natural places where rifting begins. Ancient fractures already present in the crust can be reopened when new stress develops. In this way, older structures often influence where continents eventually split. The formation of earlier mountain ranges also affected the breakup. During the creation of Pangea, massive continental collisions produced extensive mountain belts. These mountain-building events placed enormous pressure on the crust. Long after the mountains formed, the rocks beneath them still contained weaknesses, created during those ancient collisions. When stretching later began, some of these weakened areas became sites of new rifts. As stretching increased, magma started rising into cracks within the crust. Magma is melted rock located beneath the Earth's surface. When it enters fractures, it cools and forms new rock. Repeated injections of magma widened existing cracks and created additional pathways for future eruptions. Over long periods, these repeated events helped separate large sections of the continent. Volcanic activity became widespread during the early stages of Pangea's breakup. Large amounts of lava reached the surface in some regions. These eruptions covered vast areas with thick layers of volcanic rock. Some of the largest volcanic events in Earth's history occurred during this period. The lava flowed across the landscape many times, building extensive volcanic plateaus. One enormous volcanic event is associated with the Central Atlantic Magmatic Province. This volcanic activity began around 201 million years ago. It produced massive lava flows across regions that are now found in parts of North America, South America, Europe, and Africa. Today, these areas are separated by the Atlantic Ocean, but during the volcanic eruptions, they were still connected as parts of Pangea. The volcanic activity released huge amounts of gases into the atmosphere. Carbon dioxide, sulfur dioxide, and other volcanic gases entered the air over a long period. These gases affected Earth's climate and environment. Carbon dioxide contributed to warming, while sulfur gases could temporarily cool certain regions by forming tiny particles that reflected sunlight. The balance between these effects changed over time as volcanic activity continued. The volcanic eruptions also affected plants and animals living during that period. Some species struggled as environmental conditions changed. Air quality, rainfall patterns, temperatures, and ocean chemistry were influenced by volcanic gases. Many scientists believe that the intense volcanic activity occurring near the beginning of Pangea's breakup was connected to the end of the Triassic mass extinction, which happened around 201 million years ago. As rifting continued, the crust became thinner. Eventually, it became so thin that it split completely. Once the crust separated, magma rose into the gap and cooled to create new oceanic crust. This marked the birth of a new ocean basin. Water gradually filled the low area between the separating continents. A narrow sea formed first, and over millions of years it widened into a major ocean. The opening of the Central Atlantic Ocean was one of the most important results of Pangea's breakup. North America slowly separated from Africa, while South America also began moving away from Africa. These movements created space for new oceanic crust to form between the continents. The Atlantic Ocean slowly expanded as more new crust developed at the spreading center. Seafloor spreading became the main process responsible for widening the new ocean. At the center of the ocean basin magma rose from the mantle and formed fresh oceanic crust. As new crust formed, older crust was pushed farther away from the ridge. This continuous process slowly increased the distance between the continents. Even today, the Atlantic Ocean continues to widen through sea floor spreading. The breakup did not happen everywhere at the same time. Different parts of Pangea separated during different periods. Some areas experienced rifting earlier than others. Certain regions failed to split completely. These failed rifts remain visible today as valleys or basins within continents. They provide evidence of stretching that began but never developed into new oceans. One well-known example of an active continental rift today is the East African Rift. Although it formed long after Pangea broke apart, it shows geologists how continents can split. The land is slowly stretching, earthquakes occur frequently, volcanoes are active, and deep valleys continue to develop. If the process continues for many millions of years, a new ocean may eventually form there. The breakup of Pangea changed ocean circulation around the planet. Before the continents separated, ocean currents followed different paths because of the shape of the supercontinent. As new oceans opened, water gained new routes for movement. Ocean currents transport heat around the world, so changing their paths affected climate in many regions. The separation of continents also influenced wind patterns. Large landmasses affect the movement of air across the planet. As Pangea divided into smaller continents, winds changed direction in many places. Rainfall patterns slowly shifted. Some regions became wetter, while others became drier. These climate changes affected plants, animals, and the development of ecosystems. The changing coastlines created many new shallow seas. Shallow seas receive sunlight throughout much of their depth, making them rich environments for marine life. As coastlines increased in length, new habitats became available for many organisms. Marine species spread into these new areas and gradually evolved into different forms. The movement of continents also changed mountain formation. When continents collide, mountains rise. When continents move apart, valleys and basins form instead. During the breakup of Pangea, regions under tension developed rifts rather than mountain ranges. These new landscapes influenced rivers, lakes, drainage systems, and local climates. The Earth's lithosphere includes both the crust and the uppermost part of the mantle. This rigid outer layer rests on the softer asthenosphere beneath it. The asthenosphere can slowly flow because of its temperature and pressure conditions. Tectonic plates move across this slowly flowing layer. Changes within the asthenosphere affect how plates behave over millions of years. The temperature inside the Earth remains extremely high because of leftover heat from the planet's formation and heat produced by radioactive elements. Radioactive atoms naturally break apart over time, releasing energy. This continuous production of heat helps maintain mantle convection. Without internal heat, tectonic plates would not move in the same way, and continents would not continue changing position. Earth's core also contributes to the planet's heat. The outer core is made of liquid iron and nickel, while the inner core is solid because of the enormous pressure. Heat from the core moves outward through the mantle. Although this transfer happens slowly, it supplies energy that drives geological activity across Earth's surface. Scientists use many kinds of evidence to understand why Pangea broke apart. One important source of evidence comes from rocks. Matching rock formations found on continents, now separated by oceans, show that these lands were once connected. The age and composition of these rocks help scientists reconstruct ancient geological events. Fossils provide another important source of evidence. Fossils of identical plants and animals have been discovered on continents now separated by thousands of kilometers of ocean. Since many of these organisms could not cross wide oceans, their remains support the idea that the continents were once joined before separating. Magnetic evidence preserved in rocks has also helped scientists understand continental breakup. When volcanic rocks cool, tiny magnetic minerals inside them align with Earth's magnetic field. These minerals preserve a record of the field's direction at the time the rocks formed. By studying magnetic patterns on both sides of ocean ridges, scientists discovered that new oceanic crust forms continuously as continents move apart. Ocean drilling has provided additional evidence. Samples collected from the ocean floor show that rocks near mid-ocean ridges are younger than rocks farther away. This age pattern fits perfectly with the process of sea floor spreading. As new crust forms at the ridge, older crust moves outward toward the edges of the ocean basin. Modern satellite technology allows scientists to measure continental movement directly. Highly accurate instruments detect movements of only a few centimeters each year. These measurements confirm that tectonic plates continue moving today. Africa and South America are farther apart each year because of ongoing seafloor spreading in the Atlantic Ocean. Earthquakes occurring along plate boundaries also reveal active tectonic processes. Most earthquakes happen where tectonic plates interact. Along divergent boundaries where plates move apart, earthquakes occur as rocks break during stretching. These earthquakes help scientists identify active rift zones and spreading centers. Volcanoes commonly appear where plates separate because magma rises through openings created by stretching. Mid-ocean ridges contain long chains of underwater volcanoes where new crust forms continuously. Continental rifts also experience volcanic activity because the crust becomes thinner and allows magma to reach the surface more easily. The breakup of Pangea occurred in several stages rather than one single event. The earliest separation involved what would become North America moving away from Africa. Later, South America separated from Africa. India eventually broke away from the southern continents and moved rapidly toward Asia. Australia separated from Antarctica much later. Antarctica itself remained near the South Pole. Each continental movement followed its own path because different tectonic plates moved in different directions. These movements depended on forces acting throughout the mantle and at plate boundaries. The paths were not perfectly straight because changes in plate interactions altered movement over time. The breakup also changed biological evolution. As continents separated, populations of animals and plants became isolated from one another. Isolation reduced contact between populations. Over long periods, different environments led to the development of new species through evolution. This process increased Earth's biological diversity. Ocean chemistry also changed during continental separation. New ocean basins affected water circulation, oxygen distribution, and nutrient movement. Rivers flowing from different continents carried minerals into the oceans. These changes influenced marine ecosystems over millions of years. The opening of new oceans influenced the carbon cycle. Carbon moves continuously among the atmosphere, oceans, rocks, and living organisms. Increased volcanic activity released additional carbon dioxide, while weathering of newly exposed rocks removed some carbon dioxide from the atmosphere. These natural processes helped shape Earth's long-term climate. Weathering became important as fresh rock surfaces appeared during rifting. Rainwater slowly broke down exposed rocks, releasing minerals into rivers and eventually into the oceans. Chemical reactions during weathering also removed carbon dioxide from the atmosphere. The balance between volcanic emissions and weathering influenced climate through geological time. Sediments collected in newly formed rift basins provide valuable records of continental breakup. Layers of sand, mud, volcanic ash, and fossils accumulated over millions of years. By studying these layers, geologists reconstruct the timing of rifting, volcanic activity, changing environments, and climate conditions. Gravity also influences continental movement. Thick continental crust responds differently to gravity than thinner oceanic crust. As the crust stretches and thins, it sinks slightly, forming basins that collect sediments and water. These basins preserve evidence of early continental separation. Heat flow measurements reveal that active rift regions have higher temperatures beneath the surface than stable continental interiors. These measurements support the idea that rising mantle heat contributes to crustal stretching. Regions experiencing strong heat flow often contain active volcanoes and geothermal activity. Geophysical studies using seismic waves allow scientists to study the Earth's interior. Earthquakes produce waves that travel through different layers of the planet. By measuring how these waves move, scientists identify variations in temperature, density, and composition beneath tectonic plates. These observations provide information about mantle convection and the processes responsible for continental movement. Computer models have become valuable tools for studying the breakup of Pangea. Scientists combine geological observations with mathematical calculations to simulate plate movement over millions of years. These models help explain how mantle convection, slab pull, ridge push, crustal weaknesses, and mantle plumes interacted during the separation of the supercontinent. Research continues because Earth's interior cannot be observed directly. Scientists constantly test new ideas using field observations, laboratory experiments, satellite measurements, ocean drilling, fossil discoveries, rock dating, magnetic records, and computer simulations. As new information becomes available, understanding of Pangea's breakup becomes more detailed, while continuing to show that tectonic forces, mantle activity, crustal stretching, rifting, volcanic activity, and the steady movement of tectonic plates work together over many millions of years to separate the continents into the positions from which they continued moving across the surface of the Earth. About 252 million years ago, the Earth passed through the most severe extinction event known in its long history. This event took place near the end of the Permian period. It marked the end of an age that had lasted for many millions of years and brought enormous changes to the planet. During this time, life on land and in the oceans faced destruction on a scale never seen before. Many groups of living things that had survived earlier changes in climate and geography disappeared forever. The event changed the path of life and opened the way for new groups of plants and animals that appeared later. Before this disaster began, the continents were joined together into one giant landmass called Pangea. A single vast ocean surrounded this landmass. Large deserts covered many inland areas because moisture from the oceans could not easily reach the center of the supercontinent. Some regions were dry for long periods, while other places received seasonal rains. Rivers crossed the land in many areas, supporting forests and many kinds of animals. Coastal regions had different conditions from the dry interior, and mountain ranges also affected local weather. The oceans contained an amazing variety of life. Coral reefs supported many kinds of fish, shellfish, sponges, and other sea creatures. Crinoids covered parts of the seafloor. Brachiopods lived in huge numbers in shallow seas. Trilobites, which had already existed for hundreds of millions of years, were still present, although they were less common than in earlier times. Ammonoids drifted through the water. Many kinds of sharks hunted smaller animals. Strange fish with armored bodies swam through rivers and seas. Countless tiny organisms floated in the water and formed the base of the food chain. Life on land was also rich and varied. Great forests contained tall trees, seed ferns, horsetails, and many other plants. Insects filled the air. Early reptiles spread across different habitats. Some large plant-eating animals fed on leaves and stems, while meat-eating predators hunted them. Many animals dug burrows that protected them from heat and dry weather. Others stayed close to rivers and lakes where water remained available throughout the year. The Earth was never completely still during this period. Deep below the surface, hot rock continued to move. Tectonic plates slowly shifted. Volcanoes formed where conditions allowed melted rock to reach the surface. Earthquakes changed the land. These natural processes had always been part of Earth's history. But during the time leading up to the Great Extinction, some of these forces became far more active. One of the most important events happened in the region that is now Northern Asia. Huge volcanic eruptions began in an area known today as the Siberian Traps. These eruptions did not last for only a few days or even a few years. They continued again and again over a very long period. Layer after layer of lava spread across enormous areas. Rivers of melted rock covered the ground. Thick clouds of ash and gases rose high into the atmosphere. The amount of lava released during these eruptions was almost beyond imagination. The volcanic activity covered an area that stretched across a vast part of the land. As fresh lava cooled, new eruptions followed. This repeated process continued for many thousands of years. The eruptions released huge amounts of carbon dioxide, sulfur dioxide, water vapor, and many other gases into the atmosphere. Carbon dioxide is a gas that traps heat around the planet. As greater amounts entered the atmosphere, global temperatures slowly increased. Warmer conditions affected both land and sea. Some places became hotter than many living things could survive. Water sources dried more quickly. Plants struggled under rising heat and changing rainfall. Animals found it harder to locate food and water. Sulfur dioxide created different problems. It mixed with water in the atmosphere and formed acidic rain. This rain damaged forests and poisoned lakes and rivers. Leaves were harmed before they could produce enough food for plants. Young plants often died before reaching maturity. Soil also changed as harmful chemicals entered the ground. Ash from volcanic eruptions blocked sunlight in some regions. Less sunlight reached the surface for periods of time. Plants depended on sunlight to produce food. When sunlight decreased, plant growth slowed. Animals that depended on those plants soon faced food shortages. Predators then struggled because the animals they hunted became fewer. The climate became unstable. Some places experienced intense heat, while others faced sudden cooling caused by volcanic dust blocking sunlight. These changing conditions placed heavy pressure on living things. Species that had adapted to one environment suddenly faced completely different conditions. Many could not adjust quickly enough. The oceans also changed in dangerous ways. As the atmosphere warmed, sea temperatures increased. Warm water contains less dissolved oxygen than cooler water. Marine animals depended on oxygen in the water, just as land animals depended on oxygen in the air. As oxygen levels dropped, many sea creatures struggled to breathe. Ocean circulation also weakened. Normally, moving water carries oxygen from the surface to deeper parts of the sea. During this period, that movement slowed in many places. Deep waters became low in oxygen or completely without oxygen. Animals living on the sea floor died in enormous numbers because they could no longer survive in these conditions. Scientists have also found evidence that harmful bacteria increased in some oxygen-poor waters. These bacteria released hydrogen sulfide gas. Hydrogen sulfide is poisonous to many living things. If enough of this gas reached the surface, it could have killed marine life and possibly entered the atmosphere. Plants and animals exposed to high amounts of this gas would have faced serious danger. As more living things died, food chains began to break apart. Tiny floating organisms disappeared in many regions. Small animals that fed on them soon declined. Larger fish lost their food supply. Predators higher in the food chain also suffered. The loss of one group affected many others because each depended on another for survival. Coral reefs almost completely disappeared. Reef-building organisms had created homes for countless sea animals. Once the reefs died, many species lost shelter, breeding grounds and feeding areas. Empty stretches of sea floor replaced places that had once supported rich communities of life. Brachiopods experienced enormous losses. For hundreds of millions of years, they had been among the most common animals in shallow seas. After the extinction, only a small number remained. Their populations never returned to the levels seen before the disaster. Trilobites suffered their final extinction during this event. They had survived many earlier changes throughout Earth's history, but they could not survive the conditions created during the end of the Permian period. Every remaining species disappeared forever. Many kinds of ammonoids also vanished. Only a few survived the extinction. These survivors later produced new groups during the following period, but the diversity seen before the disaster had been almost completely destroyed. Crinoids experienced severe losses. Many species disappeared. Sponges, sea lilies, shellfish, and countless other marine animals also faced heavy extinction. Entire ecosystems collapsed as one species after another vanished. Fish populations were greatly reduced. Some groups survived, while many others disappeared. Freshwater environments also changed as rivers and lakes experienced shifts in temperature, oxygen levels, and water chemistry. Animals living in these waters faced the same pressures affecting life in the oceans. On land, forests began to disappear in many regions. Trees died because of heat, drought, acidic rain, and repeated environmental stress. As forests vanished, animals that depended on them lost food and shelter. Soil became exposed without roots to hold it together. Wind and rain carried away large amounts of loose earth. The disappearance of forests affected the atmosphere as well. Healthy forests remove carbon dioxide from the air through photosynthesis. As forests declined, less carbon dioxide was removed. This allowed even more of the gas to remain in the atmosphere, adding to rising temperatures. Many insects disappeared during this time. This is one of the few known mass extinction events in which insects experienced major losses. Some groups vanished completely while others survived only in small numbers. Because insects played important roles in breaking down dead plants and serving as food for other animals, their decline created additional problems throughout ecosystems. Large plant-eating animals struggled to find enough food. Many died from starvation before predators reached them. Others became weak from lack of water. Young animals often failed to survive because harsh conditions prevented healthy growth. Meat-eating animals faced their own difficulties. As populations of plant-eaters became smaller, predators found less prey. Competition for food became more severe. Many predators also disappeared as hunting became increasingly difficult. Some animals survived because they possessed features that helped them endure harsh conditions. species able to dig deep burrows escaped some of the extreme surface temperatures. Others required less food or could survive longer without water. Small body size also helped some animals because they needed fewer resources. Even for survivors, life remained difficult. Harsh environmental conditions continued for a long time. Recovery did not begin immediately after the volcanic eruptions slowed. The planet remained under stress, and ecosystems needed a very long time before they became stable again. The extinction affected nearly every environment on Earth. Shallow seas, deep oceans, rivers, lakes, forests, deserts and wetlands all experienced major losses. Very few places escaped the widespread environmental damage that spread across the planet. As species disappeared from one region after another, many ecosystems reached a point where they could no longer function in the way they had for millions of years. Living things are connected through feeding relationships, breeding areas, shelter, and the movement of nutrients. When large numbers of plants and animals vanished, these connections were broken. Even species that had managed to survive the first waves of environmental change often faced new dangers because the communities they depended on had been destroyed. Many shallow coastal waters became places where only a few kinds of organisms could survive. Before the extinction, these areas had supported dense populations of shellfish, sea lilies, corals, algae, worms, and many kinds of fish. After the extinction, large stretches of the seafloor became almost empty of complex life. Fossil evidence shows long intervals during which very few organisms occupied places that had once supported rich underwater communities. The loss of animals that filtered food from seawater changed the movement of nutrients lithophotins through marine environments. Filter feeders normally removed tiny food particles from the water and helped keep marine ecosystems balanced. Their disappearance meant that this natural process slowed greatly in many regions. Organic material settled on the seafloor in larger amounts, where it decayed and used up even more oxygen. This made already difficult conditions even worse for surviving organisms. The chemistry of seawater also continued to change after the first stages of the extinction. Large amounts of carbon dioxide dissolved into the oceans, making the water more acidic. Acidic water made it harder for animals that built shells or skeletons from calcium carbonate. Young shell-building animals faced particular difficulty because their developing shells were more easily damaged. Many species could no longer grow normally or reproduce successfully.